Good afternoon, everyone. I'm going to present a paper called A New Method for Dealing Simultaneously with Spatial Autocorrelation and Spatial Heterogeneity in Regression Models. This was a paper written by two French researchers, Geniaux and Martinetti, in 2017, so a little bit over 5 years ago. And just to give some context on the paper, they argue initially that the current traditional spatial econometric models, they fail in the presence of model specification. So they usually can't distinguish between phenomena of spatial autocorrelation or spatial heterogeneity or spatial nonlinearity. Usually these traditional models, each of them is focused on one of these phenomena only, and not the association of all of them. And they're usually restricted, like the ones that are focused on spatial heterogeneity and discrete spatial heterogeneity, not continuous. And I'm gonna explain what these phenomena are. But they propose a more versatile model, which could have various coefficients, both for the independent variables or for the spatial autocorrelation coefficient. And they propose that those can either be fixed or variable across space. And they also compare their proposed model to the more traditional ones from Monte Carlo experiments and empirical study with some real-world data. So yes, I think that can be a little bit confusing if you're not very used to dealing with spatial statistics. So I thought it would be nice to bridge eventual gaps in this sense. So first, I introduced the first law of geography by Tobler. He says that everything is related to everything else in geography and when it comes to spatial analysis. But near things are more related to each other than distant things. And of course, like geography is also like a applied social science field. So this is a little bit debatable as like a law, but this can be seen in spatial analysis quite often, this phenomenon. And it can be expressed through different phenomena. The first one that I bring forward is spatial autocorrelation. It basically pertains to how similar one data point is to the data points that are around it. It will account for that proximity kind of dimension, right? So here, for example, let me get like the laser point. So it can be measured from -1 to 1. So complete like positive spatial autocorrelation will indicate like complete clustering. So like for example, this cell is only surrounded by cells that are exactly like it. And the white cells only surrounded by white cells as well. While complete negative spatial autocorrelation would indicate dispersion. So the white cell is only surrounded by black cells, right? Completely different from itself. And like zero spatial autocorrelation would mean complete randomness. But when we're talking about spatial analysis, there will rarely be complete randomness in the spatial distribution of our data points. So while inferential statistical testing is common practice for a lot of like scientific fields, it's very problematic for spatial data because the IID premises will be very probably violated because we can't assume that on data point, one variable is completely independent from the others, and that they are identically distributed. So this is a very important phenomenon to take into account when we're dealing with spatial data. The other one would be spatial heterogeneity. It would deal with how values or processes can change, can vary across space. So discrete heterogeneity would be like very abrupt changes over space. Like you could usually see a very clear boundary of values when you plot them on the map. So for example, an urban area can be very, very distinct from like a forest area or like a residential neighborhood from a park right beside it. And you can see those boundaries, right? Just by analyzing the values of some variables. And continuous heterogeneity would indicate more gradual, smoother changes over space. And you could usually like see a gradient. So for example, the gradient from a temperature from a mountain's base to its peak. Also, for example, from the center of the city to like the suburbs, you could maybe see a gradient of services or even mobility infrastructure. And spatial heterogeneity can make it quite difficult to extrapolate or generalize patterns to a larger population. So this also needs to be taken into account. And the final phenomenon that I want to point out is nonlinearity. So it basically accounts to situations in which the intensity of the relationship between different variables may change depending on where they are located. So for example, when you analyze like real estate prices close to the beach, as you get like a block closer and closer to the beach, maybe the price will increase much more rapidly than when you are like a neighborhood away already from the coastal neighborhood. There, the price will change more smoothly, not as steeply as when you are closer to the beach. And in our paper, the authors, they argue, I think it's in the second section of the paper, and they're backed by many other sources, that these three phenomena, they're very related to each other, and accounting for autocorrelation and heterogeneity simultaneously can minimize the unwanted effects of spatial nonlinearity in regression models. So yes, now after that context, I'd like to introduce the classical models that they mentioned in the introduction. So for example, this is like a linear regression, right? Estimated with OLS. So here, all explanatory variables, they have a constant coefficient, right? So it will account for non-spatial effects, like effects that don't really deal with like distance, location differences, right? So for example, I'm gonna bring like a house price prediction case here. So what would be global variables, right? Variables that probably wouldn't be affected when you move across the city, right? So number of bathrooms or bedrooms, they would always positively affect the price, raise the price, right? Or its square footage, or the age of the building will always minimize the price of this house, regardless of where it's located. So if you are just considering these kinds of variables that are global, this could make sense to use as a regression model, but we know that it is not this simple, right? So if you want to complexify things a little bit, we could use this other regression model, geographically weighted regression. But here, all explanatory variables, they will have coefficients that will vary as you like move from space to space, and these are called local variables, right? Local coefficients, and these account for spatial heterogeneity, right? Because these coefficients, these variables, are changing with space. And now with the case, like some examples of local variables that we could say is, for example, proximity to schools in general. Okay, it would raise the price of the house if it's close to the school, but it could raise it even more like intensely in family-oriented neighborhoods, right? Where families will want to enroll their kids. Another variable like that would be like proximity to nightlife establishments. So if it's a younger populated area, that could actually be a good thing for the price, right? But if it's a family-oriented neighborhood, it will be a bad thing probably, because they want to live in a more calmer kind of environment area. So yeah, that coefficient needs to have that change, so it accounts for those spatial changes. And another case would be if the house, for example, has waterfront view. In general, that would make the house more expensive, but in luxury areas, it really raises the price much more intensely. It becomes like a premium. So yes, this one, geographically weighted regression, only has like spatially varied coefficients, but we also have like a mixed kind of geographically weighted regression, which will also include global variables, right? So it will account for those known spatial effects and the spatial heterogeneity. But here we're still missing the spatial autocorrelation coefficient, right? How the price of the house would change in relation to the price of the houses around it. So another one of the classic models is the spatial autoregressive model, which does bring that into question here. The W here is a weight matrix, so that it the price will be averaged in relation to how the prices are distributed in neighboring data points, right? So yes, spatial autoregressive model, it accounts, it has like the global variables. It has that weight matrix with a spatial autocorrelation coefficient attached to it, but it does not account for like the local variables, right? So it's missing that spatial heterogeneity aspect to it. It's not fulfilling all of the phenomena that we mentioned. And just an example of how spatial autocorrelation could be manifested in this case. As I said, like the prices of the neighboring houses, of course, they will influence the target price, right? It's a market. But in densely populated areas, that influence may be even stronger than in sparsely populated areas. So right here, that kind of heterogeneity inside the spatial autocorrelation is not accounted yet either. So this is why the authors, they propose like a kind of like a hybrid model to account for all of those potential issues, which they call MGWR-SAR. So yeah, they'll have a little bit of everything, right? Here, the auto correlation coefficient, it will vary with the location. This accounts like for latitude and longitude, just so you can understand the equation better. It will have like the global variables and the local variables, the variables that change with space, and of course the error. So yes, they propose this as a more robust regression model for spatial data. And I'm gonna go over this a little bit quickly, but just so we have this kind of context. In the paper, they bring forward the estimators that they use. So, and they compare it to like the other models, the traditional models. So of course, like the linear regression, it uses OLS estimation. It will minimize the sum of the squared errors. The geographically weighted regression, it will use kind of like an OLS estimation, but with that weight matrix applied. So it will account for the distance between the observations. And the mixed geographically weighted regression, it's a little bit more complicated. I'm not going to go into a lot of detail. But since they're using like a larger samples and they make like an empirical study, they use kind of like an alternative approach to estimate those values. And they don't go into much detail either. But they say it's a partial linear model, which they basically reduce to two steps. Like first they estimate like the GWR, and then they go for the OLS. So like the local variables and then the global variables. But with the model that they are proposing here, they utilize this estimation method called spatial two-stage least square. It's something that is not put into very much detail either. I thought it was quite dense, even for me to understand. But they use this so it corrects for the endogeneity of the variables involved. And now kind of assessing the model that they proposed. First, they make a series of Monte Carlo experiments. First, they try to see how biased the model might be for estimator parameters. When there are like variables, dependent variables, there are spatially dependent with each other. That can lead to multi-collinearity or concurvity problems. And they showed here that the mixed models, the mixed geographically weighted regression, which is one of the traditional models, and the one that they proposed, they generally perform better to account for those biases. And they do perform even better if one of, like I mentioned, that those are cases when dependent variables are spatially dependent on each other. So if you choose at least one of these spatially dependent variables to be a global one, like to have a constant coefficient, the models will perform even better. And the second experiment that they do, so basically, they claim that there are no tests that can detect if data generation process involves both spatial autocorrelation and spatial heterogeneity simultaneously. So what they do, this is also something that is a bit dense to understand, is that they compare like this is like the estimators, the rows or the estimators that they use, and they test each estimator for each kind of data generation process to see which one generally performs better. So whenever they introduce spatial autocorrelation, which is like this column, these two columns, OLS, like the linear regression, will perform, will be biased. And whenever spatial heterogeneity is introduced, so these three columns, OLS and SAR will always be biased as well. So of course, like when they match, the correspondent estimator will be more performant. But in general, one of like the alterations of their hybrid model, it generally performs better, right? So here, the more intense yellow is like the more performant estimator, and the lighter yellow is the second more performant. So it is like the more performant, of course, for itself, but also the second best performant for three other data generation processes. So yes, it appears to be more robust in general. And also, I'd like to point out that they have a third experiment, which is about kind of like an extra thing that they propose in the paper, which is an ideal way to come up with a spatial weight matrix. I don't bring this here to the presentation because it's kind of like an extra thing, but they also make an experiment with that and show that their proposal is very performant. And apart from these, the Monte Carlo experiments, they also bring forward an empirical study. They use the Lucas County house price data set. It is a known data set with spatial data in which we can observe spatial autocorrelation. And in this case, this empirical study, they only compared it their proposed model to the spatial autoregressive model, of course, because this is a case in which they know there is spatial autocorrelation. And yes, their model was it showed like 15% average improvement in their assessment. And yes, it outperformed the traditional model. But something here that I think is kind of a limitation is that I personally think that the paper could have benefited from an empirical study on spatial heterogeneity as well. But this paper is from 2017, right? And since then, they have more than 90 citations. And there are many following papers from different researchers in which they use this their model with different cases of data sets and to apply them to real data, to real case studies. And this proposed model, does have better performance. But another limitation of the paper, I would say, is that it doesn't, okay, it compares like biases as we saw here, right, errors, but it doesn't really account for maybe computational efficiency of the different models, right? What would be the estimation times required by that? And I think that would be quite a useful information, right? To know how efficient it is, their proposition. So yes, this is kind of what I wanted to say. I kind of wanted to bring more of contextualization on maybe like key spatial statistics concepts and see how they can be applied and how they can maybe skew some more traditional models, how they can be skewed by those phenomena. Since spatial data is it has its quirks, right? Has its own nuances. So yes, I think still this is like, even with these limitations, this is a highly cited paper. So I think there's a lot of potential to use it in what we do and to experiment with it. I'm going to share the slides with you. There's like the Google Scholar page if you guys want to track papers that cite this one for the case studies. And also this year, the authors, they released an INRA package for this model. and there's documentation as well. I even I tried fiddling with it for a little bit, but kind of my R skills are a little bit rusty. So I couldn't bring this to you. I'm sorry, like my experimentations, but it's something that I plan on like continue experimenting with for like further work here. So yes, I'm sorry for my convoluted kind of way of speaking. But yes, thank you.